So it's a pleasure to welcome Sam Pazicni back to our department. Sam got his bachelor's degree in chemistry and music at Washington and Jefferson College in Pennsylvania, master's and PhD in inorganic chemistry here in Madison, working with Judith Burston. Did a postdoc in biophysics and chemistry education at the University of Michigan with Brian Coppola and Jim Penner-Hahn, and then moved to the University of New Hampshire. And I noticed one of the things on his CV was that he won the James D. Morrison Early Career Award at the University of New Hampshire. Jim Morrison went to my undergraduate school, graduated 3 years before I did, then went to Northwestern, where I went to graduate school, graduated 2 years before I did, and then went on to the University of New Hampshire. And Sam, who actually we were sort of reminiscing about, worked with me on creating discussion section activities for Chem 109 in 2004.
Yeah.
So the REACH program is producing discussion section activities, but when Sam was hearing about it, it's like, hey, didn't we do something like that in the past? Yes, we did.
Much smaller scale.
And, well, yeah, we didn't do it right, obviously, because the students hated it.
Oh, yeah, there's lots of you who didn't do it right, that's for sure.
Now, maybe they were learning something, maybe they weren't, but it wasn't so much they hated it, it was that they were so uptight about these things that we almost had a riot on our hands because they had to get these things right. And the point was they were hard enough that they weren't always going to get them right. So, anyway. Sam's done a lot of things with the American Chemical Society, particularly was very active with the Younger Chemist Committee from 2003 to 2013. He's currently on the Society Committee on Education, which is the major committee that oversees all of the education activities of the American Chemical Societies. And he's also worked on ACS inorganic exams. He's currently chair of our undergraduate program coordinator at the University of New Hampshire, and he's going to talk to us about characteristics, classrooms, and curricula, 3 targets to aim for in chemistry education. So let's welcome Sam back to UW-Madison.
Thanks, everybody. Can you hear me? Perfect. Thank you, John. I had no idea about the Jim Morrison connection, so that's pretty fantastic. And thank you all for joining me this afternoon to watch me melt over the fact that the last time I stood here was 12 years ago when I defended my dissertation in front of Judith, Thomas, and Clark. So hopefully it goes as well as it did then. So let's get to it. Fundamentally, I think the goal of chemistry education research is relatively straightforward. We work to make chemistry education better for our teachers and our students. All right, it's a nice practical goal to work toward, and certainly one I've enjoyed working to since misdesigning some discussion questions for 109 a long time ago. But what I've learned is that this very simple goal can be dealt with along a number of trajectories. And so I like to think about it in terms of essentially 3 dimensions that are essentially the title of my talk. And the first thing I'm enamored with is my students. Students are great. Students are different. Students have a variety of skills and experiences and backgrounds that makes their interaction with me fundamentally different from the student that's sitting next to them. It also makes them absolutely horrendous to study because they don't behave like chemicals. All right. And so I love to study their interactions with me. I also like to study their characteristics, what they bring to my classroom. Not necessarily from the perspective that I ever want to change that. I find great value in what they bring to my classroom. I want to make sure my classroom aligns with what their experience is. So it's not about changing the student for me. It's about changing this space, the classroom. Now, I've been delighted to hear about all of the plans for the renovation of the new teaching spaces and things like that. And so none of them will probably look like the grand old lecture halls of old. But instead of necessarily changing architectures of classrooms, which you don't get to do that often, I like to think about how one can change what are called the classroom norms, how you design a course such that students have a certain set of expectations about what's going to go on. For example, exams might be individual. Or as Sissy Balin, who is a biology education researcher at Auburn, has shown, if exams have a 15-minute group component at the end, i.e. changing a norm of the classroom that they otherwise would have expected, exam anxiety goes down and underrepresented student performance goes up. And so thinking about how we operationalize our instruction in a space that looks like that can drastically change how students interact with it as well as their performance. And finally, I like to think about how students interact with chemistry content or curricula. Now, not necessarily what order should topics go in. I think in chemistry, a lot of us have given a lot of attention to whether atoms should come first or atoms should come last, or whatever Gen Chem curriculum you might want to be adopting. But I like to think about how students actively engage in these curricula, whether it be by the evidence-based practices that we adopt or something like that, or from a more fundamental perspective of how students enact in science and engineering practices, or the endemic practices of chemists, rather than necessarily some of the pedagogical techniques that we know and hear about. So with those framing ideas, I'm going to present to you this afternoon 3 different projects that sort of align in those spaces. The first of which will be looking at a student characteristic, which is language comprehension, and how we can use the underlying theory of language comprehension, or at least one of them, in order to design pedagogical interventions to help those students. I'll talk about how we alter classroom norms to ameliorate what we call student illusions of competence, and I'll describe what that is when we get there. And then finally, with regard to curriculum, I want to share with you a narrative about a project I'm engaging with the American Chemical Society, which we call General Chemistry in 3 Dimensions, or GC in 3D, a new Gen Chem curriculum reform project that we've been engaging with for the past couple of years. So let's talk about low-skilled comprehenders in general chemistry. Now, language comprehension is probably not the first thing on an instructor's mind when they go into their general chemistry class. For my colleagues, they're much more worried about a student's math ability, which I am absolutely not discounting. Clearly, students have to do math in a chemistry class. However, if we look at the language comprehension abilities of our students in general chemistry, and here's an example of this, of about 1,000 students in general chemistry at the University of New Hampshire, you can see it's quite wide-ranging. We measured this via something very similar to the SAT exam, but we gave it at the very first laboratory period of a student's very first general chemistry laboratory period. So we had a very fresh insight into the skill at the time these students were starting general chemistry. This is the average of this distribution. It also happens to be the average nationally on this particular assessment. It equates to about the 12th grade reading level. So these students at the middle are right where we want them to be as fresh people at the university. But there are this set of students that are quite below that average. And anything that's 20 to below, which I believe accounts for about 75 students in this distribution, read at a 9th grade level. And I find that quite shocking, considering that these students are now going to be challenged in college-level curricula. And so based on this, one of the first projects I engaged in my independent career was exploring how language interacts with learning chemistry. And I think there are a number of practical aspects to attend to with regard to that relationship. First and foremost, students learn from linguistic sources of information. They listen to us talk at them, or they read the wonderful active learning materials that we make for them, or they read books, they may watch YouTube videos. Still information is being given to them in a linguistic way. And so it's no surprise, therefore, that their language comprehension ability may play a role in how they're processing information that they're learning. Second, and the one that I love to play with regard to experimentation and studies, is the fact that chemistry is full of what I like to call lexically ambiguous terminology. Terminology that science or chemistry uses that also has a cousin in the vernacular language. And watching students negotiate that vernacular meaning when they first learn it in a new context, such as chemistry. So for example, does everyone know what this is? Shout it out. Ideal gas law. If you break a law, you get in trouble. You go to jail. But our students essentially find out that the ideal gas law works for what, like 3 gases? So all of nature breaks this law, right? And fundamentally, I know that's more of a funny quibble than it might be endemic to student understanding. It really comes from an epistemological misunderstanding of what a scientific law is, and the fact that that equation, right, is an actual physical model of phenomenon that occur in nature. So it's a model, right? It's a beautiful model of a phenomenon. So let's talk about that word as far as students first hearing it. Well, that's a model. It's a smaller version of a bigger thing, which is not at all what a mathematical equation is when in concert with observing a physical phenomenon. All right. Now, for a lot of students, negotiating this landscape is probably easy. But let's talk about some other terminology. We describe acids like this all the time. Why? So strong and weak in the vernacular has some sort of endemic meaning about one's, bodily or physical characteristics. I have no idea who first posited it for the extent to which acids and bases disassociate, but that's the language we use to describe it. And at least in high school students, there's a lot of work with students trying to negotiate, well, what does strong and weak really mean with regard to chemistry when I know other meanings in my everyday life? Oh, this one. That's what I think about when I think about spontaneous. One day I might just go run through a field. Not that my delta G is going to be less than 0. Or I'm product driven, however you would like to define it. A lot of students think that the reaction just happens because it's spontaneous. We also have anthropomorphizations that I love to play around with, and I think this is by far my favorite. So undoubtedly a lot of you recognize this curved arrow mechanism. What word do we use when this nucleophile reacts with this electrophile? Attack! Now, we've done research on this word, all right? Attack, especially in today's society, has an incredible connotation to it, all right? We're well aware of this word, that there are attackers, attackees. There is an active attacker. There is a passive attackee. The attack fundamentally changes the attackee. And students are bringing this idea to their knowledge of chemical reactions. The electrophile is very passive. The nucleophile is very active. It's a predetermined interaction. Obviously, there's an arrow. That's a predestination, all right? And so reaction dynamics takes a back seat to this word. At least in about the 6 or so students that we've interviewed. And the idea that the electrophile remains fundamentally changed by the attack is also within what we call a concept image. And so I find that very interesting, especially when I compare it to what students may be taking away from society as a whole these days. Oh, I could go on, but we probably know that noble gases are happy. No, they're not. They have no feelings. There's chemistry cats, which is cute. I do love a good chemistry cat. However, when the formula unit is backwards, I get really upset. Anions are not named first. All right, so we are plagued with linguistic misrepresentations or alternative representations when we deal with the language of chemistry. The last practical aspect that I will get into more today is the fact that language comprehension ability actually has a very strong cognitive grounding. There's about 9 theories, in fact, about how humans or learners comprehend language. And these range from everything about what happens in the brain of that comprehender to how that comprehender interacts with the materials that they are trying to comprehend. I'll get into that in a second, but actually I'll get into it now, excuse me. The theory that we like to, that informs our work most is strategy-based, in that high-skilled comprehenders, a hallmark of their behavior is the use of strategies to connect what they're processing as they comprehend to what they already know. All right, so prior knowledge of a domain of chemistry, of physics, will interact with one's comprehension ability quite strongly because of this ingrained strategy use. And the key is that the strategy users don't know they're strategizing necessarily. These are all implicit. And so when these types of students are interviewed, they're very unaware of the fact that they're asking questions, answering questions, formulating responses to their own questions, evaluating the worth of their own answers, or even the questions themselves. Okay? And so, that said, comprehension is built on layering knowledge that is coming in to what already exists. And so, as I've been hinting at, it probably comes to no surprise now that language comprehension ability is highly correlated with chemistry performance. This slide is simply representing a bunch of different ACS exams, a bunch of different ways to measure language comprehension ability, the Gates-McGinnity test that I showed before, SAT verbal scores in another experiment, and all of the Pearson correlations are of moderate effect. The same size effect is if you give a mathematics test and correlate it to performance. So, one of the first ideas that we tackled with regard to exploring language comprehension in the general chemistry classroom is to go back to this idea of the connection to prior knowledge. And so if deep comprehension emerges from a student's strategy use of connecting prior knowledge to comprehension ability, perhaps it's a reasonable hypothesis that one's comprehension ability could compensate for a lack of prior knowledge. I find this hypothesis very attractive because in my general chemistry classroom, I have 300 students who all have 300 different backgrounds in chemistry. Some of them are quite weaker than others. And so if I can capitalize on a characteristic that some students have, perhaps I can build in things that will help those students differentially. And so we collected the following data, some exam scores at the end of the semester. These were ACS exams at the end of the class. We gave the ACS Toledo exam at the beginning of the course to measure their prior knowledge, and we also measured their language comprehension ability, again by verbal SAT scores as well as the Gates-McGinnity test. And I parsed this data out such that high reading ability or language comprehension ability are these two lines. This is modeled so that that's one standard deviation above the mean for whatever measure we're using, and the solid lines are one standard deviation below. And so automatically you can see the learning gap between high and low skill comprehenders as a function of the standardized ACS exam score. So these are simply standard deviations. But what I'll call your attention to are the slopes of these lines. So there is a point, for example, on this line where you can have high enough comprehension ability, maybe starting here, let's say, where you begin to achieve the same as a student with high prior knowledge. And so the slopes of these lines are stacked just right so that one's comprehension ability can at least partially compensate for a lack in prior knowledge. And I'll tell you from looking at other variables like this, sometimes these lines are just flat and there's no compensatory ability whatsoever. So it's actually very nice to see that we can have one characteristic compensate for another. Now back to our cognitive grounding. We thought, well, if these low-skilled comprehenders are not employing the strategies that separate high-skilled comprehenders from low-skilled comprehenders, well, let's just make them. Let's build into the class a pedagogical manipulation such that everybody is required to adopt a strategy that we know is aligned with good comprehension. So we implemented a multiple questioning strategy throughout the semester so that the course's learning objectives were tested a couple of times prior to the eventual assessment to see if generating those questions among our students was going to have any effect differentially for our low-skilled and our high-skilled populations. And so we layered on this another question, what kind of questions are better? And we pit two popular ones against each other. First of all, there were multiple choice questions. Really easy to implement, really easy to grade. Some of us don't like multiple choice questions because they don't show potentially good assessment characteristics. However, the work that I'll quote from Bjork and Bjork here actually shows something really fun, which is that students learn a lot from engaging in multiple choice questions. They learn not only what to associate with the stem of a question with a correct answer, but they also learn how to disassociate the alternatives in the question with the information given in the stem. So there's actually rich learning there rather than necessarily rich assessment. But mainly, we were going after these because they're very easy to evaluate. We pitted these against sort of a gold standard in language comprehension, which are called elaborative interrogations. They're open-ended why questions. And so, for example, students, periodic atom size decreases across the periodic table as you go from left to right. Why? And they would enter text within a field on their computer. These are shown time and again in the literature to allow students to connect what they know with what they're learning and have been shown to be quite useful in helping students comprehend. But they are terribly difficult to grade because you have to look at writing and you have to look at writing samples weekly from 200 students. And that's not very instructor friendly. So hopefully multiple choice will win out. And so when I say learning objectives, you probably know what I mean. They're simply lists of things that the students should learn. In addition to be a learning resource, we used it as a research resource because we coded the class and everything that went on with it according to these learning objectives. And so every quiz, every exam item, so on and so forth, was coded to one of these by individual raters so that we could enact the following research design, a learning objective-driven research design. We were able to manipulate at the level of the learning objectives rather than manipulate at the level of classes. And here's why I think that's important. When you take one class and put it against another class as far as measuring performance in an experiment versus a control, well, that's really hard to do in a very authentic setting. All right. The mere fact that one class could be at 8 a.m. versus the other class at 10 a.m. could account for some variance within that population, right? Also, what if you're at a smaller school and don't have access to two groups? Can you really establish that those two groups are equivalent? You can give every measure under the sun, but you still are never going to account for all of the differences necessarily between those two groups. Finally, I don't think it's particularly ethically sound to treat one class differently than another, especially with something that you think is going to show improvements in learning. All right, it amounts to a medical trial whose experimental medicine went well over placebo. Right, the trial is stopped and everyone's given the experimental medicine. And so I think we should take the same lead in education research and not treat classes differently from one another. And so we argue that experimental manipulation at the level of these learning objectives will allow a within subjects design so that everyone is treated equally and we can get around these issues. So here's how we employed it. We chose 18 learning objectives randomly out of a hat. Literally, I made my grad student pull them out of the hat. I thought it would be fun. And we partitioned them into 3 groups. 6 of these learning objectives were going to be quizzed twice with multiple choice questions before an assessment. 6 were going to be quizzed twice with elaborative interrogations before that assessment. And then 6, and these were all going to be deployed online. I think we used Blackboard at the time. And 6 were going to be not quizzed to serve as a control. There is a time on task issue there, but from previous work in other groups, it's been shown that simply doing a timed control, like read this for 5 minutes or something like that, really shows no difference than doing it at all. So we just went with the easier option. And we folded these into 18 question exams with open response questions conducted over 2 terms with 4 exams per term. Whew. 72 pieces of data per student. So this was a fun data analysis problem, and here's how we dealt with it. All of the exam items were graded from 0 to 5, and so that made the distributions of those scores relatively non-normal. So to do any type of statistical analysis, we had to take care of that first. And so what we ended up doing was, for exam 1, for example, those 6 learning objectives that were priorly quizzed by multiple choice, we just meaned them. And that made the distributions work out toward normality. So that was an easy fix there. So all of this data were reduced to 12 exam subset means that were indeed normally distributed. And then these subset means are going to be used as the dependent variable in our analysis. Now, the next problem we encountered is that these data are what is known as possessing a nested structure. They're not independent of one another. So we're having multiple observations of the same student throughout the semester. And this violates assumptions of independence in statistics. What that means is that in regression analyses, we try to keep track of the variance in the population. Our models always want to explain the most amount of variance as possible, but we want to know the explanation of that variance. When data are nested in structure, we don't know what level that variance is being pooled. And so we have to do a trick here as well, which is to adopt an analysis called hierarchical linear modeling, which is essentially a fancy regression. So here's how we do that. We write a regression equation, so predicting our outcome variable with an intercept and a bunch of slopes that correlate to our within student characteristics. And so this is whether that subset mean was quizzed via EI, multiple choice, and then the time in the semester that happened. And then we take each of that intercept and each of those slopes and write equations to predict those from our student level characteristics, comprehension ability, and their prior knowledge. All right? And then we do an analysis on this set of equations to back out the statistically relevant parameters. In the way that I've coded this, B1, beta 1, 0, beta 2, 0 are going to be the main effects of questioning. So how multiple choice did overall, how elaborative interrogation did overall. Beta 1, 1, beta 2, 1 are going to be the moderation effects of comprehension ability. To what extent did these question types differentially aid those of low or high comprehension? So, after statistical analysis, these ended up being our statistically relevant parameters. So, to go through this model, beta 0, 0, the grand mean of everything. A student of average prior knowledge, average comprehension ability on the control items of the analysis. So after all of that is said and done, those exam subset means are about a 66.31. And now what we're going to do is add the effects on sequentially of the other statistically significant parameters. If someone was high-skilled comprehender, they improved in performance by about 4 percentage points. Interestingly enough, prior knowledge didn't end up being a statistically significant parameter here. Oh my gosh, I'm really sorry, it was. Whew. So you add about 7 points if you're higher in prior knowledge there. My apologies. Time, things didn't change much over time. That would be beta 3.0 here, only about 0.9 across the semester, so we're not going to worry about it. The effect of elaborative interrogations was negative. You actually decreased in score when you took those questions, just by a little bit. I'll get into that shortly. Multiple choice questions, a positive effect. Beta 2.1 ended up being significant. Remember, that's the moderation variable. So this negative value means that these multiple choice questions aided the low-skilled comprehenders more than the high-skilled comprehenders. Enough statistics, let's look at a plot. Comprehension gap, we've talked about it before. Elaborative interrogation questions didn't do much for either population. In fact, it went down just slightly. These means were calculated by a different mechanism, and so you're really not seeing that difference in these plots. Multiple choice questions closed the gap and raised everyone's performance. So we're finding that indeed adopting that theoretical strategy of multiple questioning in this class is helping out these low-skilled comprehension students. Now, what happened with elaborative interrogation? Serendipitously, a beautiful paper came out about 2 months after we published this, of course, that talked about testing effects like this. The idea that if you test things over and over again, students are going to do better later. That's been known since about the 60s. But what hasn't been known is the effect of feedback on that particular effect. And it was Bjork and Bjork again from UCLA. They showed that when students' feedback is delayed or non-existent, testing effects go away. When feedback is immediate, testing effects stand. Elaborative interrogations I mentioned earlier, we couldn't grade them fast enough. Also, we didn't even know if students went back into the system to see any of that feedback. But multiple choice questions were immediate. And so we think that's what's going on. We just need more work to prove it and look at other question types potentially to see if they have any enhanced efficacy. So, with regard to student characteristics, I hope I've shown you that measures of language ability are important to consider. They predict general chemistry performance just as well as math measures, and we have a theoretical basis with which to work with in designing classroom interventions to handle that particular characteristic. And students with high language ability, we want to cultivate because that can really, or at least partially compensate for a lack in prior knowledge. Students with low comprehension do not employ strategies like high comprehension students, but if we can build into our classrooms and make them employ those strategies, at least with multiple choice questions in our research scenario, we see that we can differentially aid those particular students, closing the gap from 11.1% to about 5.6%. In the context of this class, that was half a letter grade. Let's talk about classroom norms next. Overcoming what we like to call illusions of competence. Now, like anything, I think Shakespeare put it best. It's one of my favorite Shakespeare plays, As You Like It. It's the court jester, Touchstone, talking to William, a country boy, ironically from the court jester saying, "The fool doth think he is wise, but the wise man doth know he is a fool." That is to say, those who are most confident in their level of expertise aren't necessarily those who should be. Considering today's political climate, we probably know this quite well. However, this is a recently characterized phenomenon in psychology known as the Dunning-Kruger effect. And it's a cognitive deficit that plagues the unskilled in any domain of knowledge, such that the poorest performers are the ones that are the least aware of their own incompetence. In the original literature, these plots were made. I'm going to show quite a few of them in this section of the talk, so I figured I'd show you the very first one ever made, such that there are two lines here. One in solid line is a student's perceived ability. In this particular experiment, they estimated how many of their peers they were better than, according to whatever was being tested. And then the lighter line is their actual ability, independently rated. The means are binned into 4 quartiles, such that the bottom is the lowest quartile and the top is the highest quartile. And you can see that actual test scores and the bins on the x-axis are linear, but the perceived scores are of a different slope than the actual ability, such that the students, or excuse me, the test subjects are at the bottom are greatly overestimating their own ability, whereas the top students are underestimating their own ability. The psychology, the literature battle about this effect in the literature over 10 years was phenomenal. I've never read such cheeky literature articles in my life. And so it's a fabulous story to sort of run the course. But in general, we do believe this phenomenon. It's not just a general regression to the mean phenomenon, especially because of a really cute study that Kruger had done. What he did was present students who are up on this end of the graph, work of their lower performing peers. And then they asked those students, well, now what do you think your relative ability is? And those students went, oh, this is awful. I guess I really am good. And they much better calibrated to their own ability. Students down here were similarly given work of their higher performing peers. And they go, well, this is the same as mine, right? There's no difference, because they don't know enough to know what they don't know, or they don't know enough to necessarily critique work of others and recognize it as actually better or worse. And so that experimental manipulation really showed a lot of people that this was a particularly real phenomenon. And it's been replicated in a lot of situations. This study right here was everyone has that friend who thinks they're funny, but they're not funny. So this is actually a plot of people's perceived humor versus their actual humor rated by expert comics. This has been replicated in gun owners' knowledge of gun safety. Ugh. And medical students' knowledge of surgical skills. It makes it, right? You don't want to leave the house. But you bury those feelings deep and you move on with research. And what this effect really hadn't been taken to is the STEM classroom in a large scale. And so my colleague at UNH, Chris Bauer, and I ventured onto this in Gen Chem to do the first large-scale STEM study of this phenomenon. And so we collected data from 9 General Chemistry 1 classes, that's very similar to Chem 103 here, and a couple of chemical principles for engineers. The closest thing here at UW is 109. We had some great populations to work with, but these courses weren't necessarily special. They were traditional lecture lab formats. Exams required written problem solving. None of them actually required many multiple choice questions, or were nothing but, so at least some were combinations. Our populations were actually inverted, so that was fun to study. Our Gen Chem 1 is predominantly female because of the service to the biologically and medically related disciplines, while our engineering course is the opposite and predominantly male. So 85% male students in that case. So we had good sex balance in our overall data. And so we can measure this phenomenon in 2 ways. We did it by putting exam questions for bonus points at the end of exams. By the way, it doesn't make any difference if you put them before the exam or after the exam. But we asked students things like, how well do you think you performed on this exam in comparison to other students? I think I performed better than insert number here, circle number here, something like that. And we achieved the same Dunning-Kruger pattern. This is an outward estimation. The students are comparing themselves against their peers. We can also do an inward assessment by having them predict their raw score. So that idea of peer competition isn't within the experiment, simply by asking them, how many points will I receive on this exam? Circle it, write it, whatever. Same pattern. All right, so this phenomenon is robust to the measurement techniques that we're using as well. Now, what I'm going to do first is, unlike the last section, let's explore the data first and then dive into the statistics. So these are the Dunning-Kruger plots on the 9 general chemistry classes, just to show that instructor, time of day, semester, fall or spring has no influence on this phenomenon. Yeah, sure, there's some variability along these lines, but in general, everyone here in the first quartile is overestimating, everyone in the upper quartile is underestimating. So we really don't see any distinction between when or what the class is or who's teaching it. The effect of sex followed along with what we know psychologically about how male students perceive themselves with respect to female students. And so our male students are always overestimating themselves more than our female students, and at the top end as well. However, the phenomenon with respect to the Dunning-Kruger effect is the same. Both female and males overestimate themselves at the bottom and underestimate themselves in the top. And so I would say here that there's really no effect of sex other than what we already know about the impressions of students have themselves based on whether they identify as male or female. The last question that we wanted to look at essentially was from the perspective of an instructor, because we give students these exams back. And in this case, they were getting not only an exam back, but their own prediction back, right? And so we want to think as instructors that we're doing our students services by giving them feedback, and they're going to use this feedback. Oh, wait, we want the unskilled to adopt different strategies, different learning techniques, or just come to my office hours, please, right? So do perceptions change across a semester with the feedback that we normally give them? Because we're essentially telling the incompetent that they're incompetent. We do that with that letter grade, right? No one gives an F-. I just thought it was cute. But you probably see where I'm going with this. So here's exam 1 in red, exam 2 in green, exam 3 in blue. Uh-oh. The way I'm showing these data is slightly disingenuous because I'm not taking into account if someone was in a lower bin in exam 1 and moved upward across the semester. We're going to get to that trajectory analysis in a minute, but you also might realize what's coming in the declarations in my voice. So, let's move on to some statistics. And so, as before, we're making multiple observations with our students. So we're violating all kinds of regression techniques. We have to go back to these hierarchical linear models once again. And so here's our within student equation. MCI here is a little trick that we did. It's simply the extent of miscalibration. We call it the Mis Calibration Index. Essentially, how well they thought they did subtracted from how they did gave us this number, such that overestimations were positive in value. And we're going to predict that with the within student characteristic, which is simply performance over time. And then we're going to predict this intercept and this slope from student characteristics of sex, as we talked about before, as well as their overall performance in the course, which was taken as just their exam average. These were our statistically significant parameters, the things that predicted the intercept, not the slope of time. So what this means is that even though the analysis I showed you before didn't take into account student hopping, this shows that no student slopes across the semester are anything different than 0. I was flabbergasted. I stayed up till 2 in the morning one night and I plotted every student trajectory, all 1,137 of them. 36 changed meaningfully, either up or down. All right. Student perceptions of themselves are not changing across the semester. And just for the numbers, as far as the mean of a man with an average exam average, that was 7.2. The effective sex, if one was female, that decreased about 4 percentage points, again signaling that females underestimate themselves relative to males. And then the rather large effect of exam average, such that lower skilled exam takers are greatly overestimating their own performance. And this goes back to an original conclusion by the Dunning and Kruger team. Poor performers do not learn from feedback suggesting a need to improve. So as an instructor, what do? Because we sort of rely on that exam feedback, right, for students to make good choices about what they're going to do. But there's actually a problem with feedback. The feedback paradox is my terminology. No one said that, and I don't know if anyone else said it, but I liked it. The paradox is that, well, as we probably know, feedback is well known to be very important for student learning. The rub is that students either don't use it or don't know how to use it, and the latter is actually more documented than the former. All right, students either don't have enough knowledge to engage in the feedback that we're giving them. It is a little bit psychologically detrimental to really think about how bad you did, and therefore students stay away from it. Or in a couple of cases, oh, no, just give me the answers, is also documented. And so we came up with what we thought was a good way to help these students who are willing to engage in that feedback, but didn't necessarily know how to, or needed a starting point. And so we intervened on behalf of these low-skilled exam takers, such that they could more meaningfully engage in the course feedback we were giving them. We adopted what the literature calls a feed-forward strategy rather than a feedback strategy. Feed-forward means that something is coming after giving the exam back, or the feedback. All right, it's going to be used in a forward-thinking process as a further endpoint in the assessment process, rather than that exam being the final point in that. So in that Principles for Engineers class, we came up with a reflective writing assignment that allowed students to reflect on whatever feedback they got on their midterm exams. This amounted to, well, what did you do wrong? Why was it wrong? What could you do better next time? Or if you had a chance to retake that exam, why would that new answer be better? And maybe how can you change your studying so that this doesn't happen again? All right. So students, for every section of the exam that did not receive full credit, they had to address these issues. And it could be, I made a simple math mistake. And that's fine if it was a simple math mistake. But if you didn't understand what effective nuclear charge was, I want you to be honest about that one. And that's not a simple mistake. And so there was some training involved with getting students to answer these questions. But we did sort of control the situation such that feedback was only given it's called task feedback. No right answers were given, but a score out of 5 was given, as well as hints. Think about this, think about that, think about this concept, think about your use of that equation. And an instructor-generated key was also never generated. The carrot here, to help our lowest skilled performers, was that 33% of the unearned points could be achieved back. So if you lost more, you had more to gain. If you lost 1 point and wanted that perfect 100, well, you would never get it because you got a third of a point back. Here's the structure of our data for exams. This self-assessment was done in betwixt each exam. So the first self-assessment would happen there, and that's how many students completed it in the course of our study. That was the second one. That was the third one. There were very mild correlations between who did it once and who did it a second and who did it a third time. Reasonable enough so that different populations were doing it each time. And then these are the data that we collected at each time point. An exam score that we standardized to look across different semesters, as well as, again, those two measures of perception, the inward measure and the outward measure, so 2 MCIs. Let's explore the data first. So this is the exam 1 to exam 2 perceptions measured by the outward assessment. What percentage of the class did I do better than? So here's how those students did on exam 1. Green is those who performed the reflective activity. Blue is those who did not. So those who chose to perform it were the exact students we wanted to target. Those who were greatly overestimating their own performance, i.e. those who were not doing so well in the class. Those who did not do the self-assessment really didn't need to. So they did that on exam 1, and then they took exam 2, entirely different material, and their perceptions now coalesced with each other. So they learned to be a little bit more self-perceptive after doing this activity, apparently, or at least these data suggest. This is repeatable. Here's exam 1 to exam 2 again. Here's exam 2 to exam 3, exam 3 to exam 4. The slopes are getting a little less. The error bars are getting quite monstrous. And so we'll parse that out in some later stats analyses, but we're seeing the general trend that's going on here. And these exact same patterns happen when we use the other measure of MCI, the inward measure. But let's take a look at performance. It's going to be inverted now, because those students who chose to do the self-assessment were approximately a standard deviation below the mean in these classes. Those that chose not to were a little bit above the mean, and their performance on the second exam also increased and caught up to those who did not do that self-assessment. This makes sense to me, because if you're able to better predict how you're doing, you know more. Here's exam 2 to exam 3. Exam 3 to exam 4. Again, same story. Slopes are getting suspect. Error bars are getting extravagant. So let's do some stats. You've been through 2 hierarchical linear models so far. So let's go for a third one. How we did this was our outcome measure, whether it was MCI or whether it was exam performance, was determined on the student level, essentially by time, exam 1, or self-assessment, exam 1, exam 2, exam 3. And then those slopes and intercepts were predicted by the self-assessment that they chose to do or not do. And we were also able to control for prior knowledge, because that may have a strong effect on this phenomenon. And we were most interested in change over time, because the intercept is time 0. They didn't do a self-assessment yet. So when the outcome was exam performance, these were our statistically significant parameters. So a statistically significant intercept here meant that there was a nice change over time in the general population. All right, to the extent of, or at least there was a statistically significant one, of negative 0.04. That's standard deviation, remember, not raw performance. So it's going down slightly across the semester, but nothing that I think is cause for concern. That first self-assessment boosts folks' performance by 0.1 of a standard deviation, essentially. The second self-assessment about 0.05 of a standard deviation. And so we're seeing how this is affecting statistically significantly change over time, with only self-assessment 1 and self-assessment 2 being the statistically significant parameters. So, with regard to this, hopefully I've shown you that we've done some work characterizing students' illusions of competence. Alarmingly, these perceptions do not seem to change across the semester, despite the fact that we directly tell our incompetent students that they're incompetent by the exam grade that they get. Overall, choosing this feed-forward strategy seems to work, and we're able to target our students plagued by illusions of competence, and that early feedback, early reflection in the semester seems to be a lot better than later in the semester, at least how our stats are working out. I think we would need to do some more modeling in order to tease that out more rigorously, but overall, we're seeing that slope and change over time being affected early in the semester. And I'm going to skip that and leave it for another day. The last thing I'd like to tell you about this afternoon is our work with the American Chemical Society about general chemistry in 3 dimensions. And so this is essentially an effort for general chemistry course reform based on evidence-based content reform rather than evidence-based pedagogical reform. And so in 2018, we know a pretty good amount about how humans learn. And if you've never read it, Brain Mind Experience in School, How People Learn is a fantastic book put out by the National Academies Press, who basically say that engaging students in the practices that you do as a discipline will deepen those students' learning of that particular content. And this happens for a number of reasons. First of all, experts in a discipline organize their knowledge around essentially core ideas of the disciplines. All of us think in terms, or many of us think in terms of, here's what's happening thermodynamically with this situation. Here's what's happening molecularly, structurally. Here's how that influences properties. We have these grand ideas that we tend to reason with in most of the problems that we deal with. Why aren't we teaching our students to do the same thing, for example? Engaging students in the practices that we undergo actually allows them to transfer knowledge to different situations, different practices that they might encounter, which is also going to encode learning at a deeper level. And finally, students' epistemologies will deepen. Their knowledge about how the knowledge was generated in the first place. They can see through our practices how our knowledge was generated rather than just reading what happened 100 years ago in a textbook. Who reads? Watching a YouTube video. So we're going to attack this in a different way than what is normally done these days. You attend workshops and you learn evidence-based pedagogical techniques or evidence-based practices. Those are great. There's a lot of evidence behind them. Sometimes, however, they're taught in such a way where the deep knowledge of the learning theories behind those evidence-based practices are missed. And so when they are implemented in the classroom, faculty can make choices that render them a little bit or completely ineffective. And that's been documented in the literature. We're going to come at this where faculty are arguably a little bit more comfortable thinking about the content of their own discipline and the practices of those disciplines. And so you might ask, well, has anyone thought about the big ideas of chemistry? A lot of people have. What we adopt is something from the American Chemical Society Exams Institute that documented what's called the Anchoring Concepts Content Map. This is a little hard to read, I apologize, but central to this map are the big ideas of chemistry. Atoms, bonding, structure and function, intermolecular interactions, reactions, visualizations, experiments, equilibrium, kinetics, energy, and thermodynamics. And so this was an amazingly elaborate process that took thousands of chemistry educators to develop, and they landed on these big ideas. And so I think we'll trust them. As far as practices are concerned, a lot of folks document the practices of chemists, but for a general chemistry class, which is only going to be an introduction to chemistry practically for those who are going to major in chemistry, about, 5% of our students, we focus more on a general introduction to science practices that we can find in a framework for science education, which is the basis for the next generation science standards in the K through 12 curriculum. They're easily adaptable to higher education situations. There's no reason why they just need to be used in the K through 12 arena. And so, for example, science and engineering practices, one that chemists love is developing and using models. This is what we do, right? Whether they're molecular models or mathematical models, not tiny planes, but physical models, this is something that our discipline is based on. And so I argue that our students should be doing that, right, as a fundamental scientific practice. The third dimension are cross-cutting concepts, also dictated by a framework for K through 12 education. These are explanatory devices that work across fields. All right, so students begin to understand what are the dominant explanatory things in science, rather than just in a particular discipline. And this can be pattern recognition, cause and effect mechanisms, systems and system models once again, structure and function, which actually goes well beyond chemistry into biology as well. And so uniting these three dimensions is our goal here. And a deeper reason that we're doing this is because if we think about inquiry, that word has been dominating higher education for about 25 to 30 years. And I guarantee you that if you ask three people what inquiry is, you'll get different definitions about what inquiry is in the classroom. But if you think about scientific inquiry, it's doing these things. It's making a model and investigating that model for a phenomenon. It's reasoning mathematically. It's obtaining, evaluating, and communicating information. So we argue that these scientific practices are essentially the disaggregated components of inquiry. If you're doing these with your students, you're doing inquiry and you're doing active learning because these practices, by definition, are also active. So, I'm not making this curriculum, actually. I'm helping others to do it. All right, so the pathway we decided to take came out of a joint committee meeting that lasted about a year at the American Chemical Society. And I think a very smart decision was made that a group of people shouldn't get together and dictate to the chemistry community how this should be done. All right, we should work in a distributed but coordinated process so we can understand how this can be implemented across different types of institutions so that we can afford disciplinary context in this conversation. We're not going to make the next generation science standards for chemistry. We're just going to give faculty the tools to implement this in their own contexts. So, we had 2 workshops sponsored by the ACS, thankfully, in 2016, 2017, and faculty gained experience with a framework for K through 12 education, as well as evidence-centered design principles. I'm running out of time, so I'll skip that. But faculty created what are called learning performances that they were able to use in their home classrooms. Learning performances are profoundly different than learning objectives. Learning objectives tend to say what a student should know. A learning performance says what a student should be able to do as a result of knowing something. Really different. It's very practice-oriented. It's very actively oriented. And so we've been working with some wonderful institutions. Here's 2 examples of them. I'll go through Professor Adrian Vialta Cerdas' example here, where he combined the disciplinary core idea of molecular collision theory, the cross-cutting concept of cause and effect, and the science practice of developing a model to create the learning performance, again, what he's expecting his students to be able to do, which is given kinetic data from a series of reactions, use models of molecular motion to explain vibrations and variations in reaction parameters, which causes the observed kinetic data. So that is the task that he's going to give his students to do. They're going to do something with what they've learned rather than just summarize kinetic molecular theory. And then this is an example of the evidence that he's expecting his students to generate that would serve as evidence for students performing that particular task. And so here's another university. We worked with about 10 universities in doing this, and we're getting up off the ground in implementing this in their classrooms. And so I like this quote to summarize what we've been doing here. I like it because it's as old as I am, which is 39. We should be teaching students how to think instead of primarily teaching them what to think. And I think we're trying to achieve that ideal by engaging students in scientific practices in addition to engaging them in content. And this is what's motivating our general chemistry reform. We want to expect our students to do something with what they know, teaching them how to think rather than teaching them what to think and simply sometimes regurgitating that. And so I have some people to thank for all of this work. Dan and Renee were my two Chem Ed PhD students so far in my career. They did the majority of the language comprehension work, as well as a lot more I didn't get a chance to talk to you about. And we've done this through funding from what's known as the Davis Foundation in New England, which gave a big grant to our Center for Excellence in Teaching and Learning that I draw funds from. And the director and assistant director there, Victor and Elizabeth, have been a great help on that front. The Illusions of Competence work was done with my colleague, Chris Bauer, at the University of New Hampshire. GC in 3D is a really wonderful collaboration between the ACS, Ashley Donovan is our staff liaison, and then myself and Don Wink from the University of Illinois, Chicago. And so that's what I have to tell you about characteristics, classrooms, and curricula. It's great to be back. I've had great conversations today, and I look forward to your questions. Thank you very much.